morning, everyone.
Morning.
If I can get this to come up. Good morning, I'm Steven, no wait, not Steven Stahl, Nathan Crane. I looked in the mirror this morning. And this brief overview of force balance mechanisms and a few pneumatic principles. I am a strong proponent of pneumatic instruments, as you may well know. And the answer to question number one is, it helps if I pass it off the question. I got a little ahead of myself.
I was afraid it was going to be a test.
There you go, would you want to pass those around? These are discussion questions as before. I wrote out your notes for you, so the purpose of these questions is for you to write down an answer that makes sense to you throughout the discussion of this topic, so that you can refer back to these notes if you ever have a pneumatic transmitter or a force balance instrument that you need a little brushing up on. And that sheet should be a good briefing for you to get ready for the job. So the answer to question number one, as I so bravely went into, this is the main reason that I like pneumatic transmitters and pneumatic instruments in general, is that you can't short them out. You can't shock, they can't shock you, you can't blow a fuse, you know. They're impervious to all kinds of different things. And to an extent, they're indestructible unless you're trying to destroy them, you know. The purpose of this class is to introduce the student to force balance instruments. I'll be using the Foxboro 11GM as an example. I will explain the operation of a flapper nozzle, pneumatic relay, and the effects of negative feedback, as well as preload on a lever. I will also describe some simple techniques on how to troubleshoot and repair pneumatic instruments. Examples of force balance instruments, you'll notice that is question number 2. Force balance instruments are any kind of force balance. Take, for example, a seesaw. If you remember, if you're opposite of someone who is bigger than you are, they have a bracket where you can change the fulcrum of the seesaw so that you can still play, and that is where we get into this. Force balance instruments rely on this principle of being able to balance whichever force is presented. Now, if we were trying to weigh someone, then we would want one side to stay the same. But in the purpose of this transmitter, our output is going to change. So we can have forces of different oh man, I just lost my train of thought there. Forces of different magnitude, that's the word I was looking for, on either side. This is our 11GM, and the reason I picked this transmitter was, number one, I had one available to me. We took this one off of a nitrogen cart. And the fact that everything is out in the open where you can see it. When you look at this transmitter, you can see the force bar, you can see the range bar, you can see the flapper nozzle, you can see the relay. Everything is right there, so it's a good demonstration model. And the way I like to go through this is to start at the pressure connection to process and work our way through the feedback bellows. So this picture, as you can see, is just vented to atmosphere. There's a screen down here on the bottom in this drawing. This transmitter in my hand, it actually has a low side on it. It's meant for measuring DP, where you can pick the low side. This one is always referenced to atmosphere. So this is more of a pure pressure transmitter and not a differential like this one. Even though, as we all know, all transmitters are differential pressure. It's just a matter of what you're referencing to. But you'll notice on your notes sheet in the drawings on the front, there's a chart down at the bottom that shows the different pressure cells. There are 5 different varieties of pressure cell. And the reason I put that chart on there is to show you that as the pressure cell pressure increases, you know, you see 10 to 80 and all the way up to 200 to 2,000. As the pressure rating goes up, the size goes down. That is to say that from here down is the only part of the transmitter that cares what the process pressure is. Everything up here is strictly force balance. And what I mean by that is, take for example, if you're using the A capsule. If you're using the A capsule within the pressure span that is designated, it will have the same amount of force on the bottom of this force bar as if you were using the E capsule in the E range. That's the reason the pressure cells get smaller as they increase in pressure, so that it'll exert the same amount of force on the bottom of this bar. And in this example right here, the force bar is this big stainless steel bar that runs right behind the relay. It goes all the way down into the pressure cell. This diaphragm seal is the fulcrum for that lever. So you can see, if you remember back from a few slides ago, we've got a small lever over here and a much larger lever over here, because we're looking for a very minute change in the position at the bottom of the force bar to create a larger change in motion up here. But all of these movements are so small that you can't really see them. Even if you had this thing in a stand and hooked up and were changing the pressure, you would just notice the output tracking the input. Well, now that we've discussed the pressure cell, we'll move up to the flapper nozzle. The flapper nozzle is connected to the force bar by a flexure. And you'll notice the last question on your discussion question, number 20, is what is a flexure? Well, it's this thin piece of metal. There are several flexures in this device, and a flexure is just a thin piece of metal that will allow force to be transmitted, but it will also compensate for torsion. For example, if you have 2 levers, such as the force bar and the range bar, and they both try to pivot, they're going to have a little bit of torsion to them. Now, I'm exaggerating the movement, but the flexure allows for that torsion. If you were to put a piece of bar stock across there and bolt it down, you wouldn't have any movement. So that is the definition of a flexure. It is something that allows force to be transmitted from one element to another, but allows for torsion in the 2 elements. So as this force bar, you notice the pressure is going from left to right in the drawing. So the force bar, since it has a fulcrum at the diaphragm seal, there should be more sheets back there.
Right here.
The sheets are on the table there. As this force bar moves from right to left, because of the fulcrum, we all know how a lever works, so we're pushing this way on the bottom, force is going to be this way at the top. It's going to move that flapper closer to the nozzle. And the purpose of a flapper nozzle, which is one of your questions, I don't remember which one, the purpose of a flapper nozzle is it's a way of transforming mechanical motion into a pressure signal. And the way we get a pressure signal on this flapper nozzle is the air supply comes in and it goes through a reducing tube, which I can show you right here. The Foxboro, they made this thing real simple so that you could get the reducing tube out. The reducing tube has a very small orifice in it. It's on the order of 5/10,000ths of an inch or so, which is one of the answers to number 12. You can clean the restriction with a .0005 inch wire. This is the reducing tube. I took it out of this port right here. It just looks like a screw, but if you look on the bottom of it, it's got a little piece of plastic with a very small hole in it. I can pass that around so you can look at it. The supply pressure enters from the sides of it. It has two big holes on the sides, and then it goes through the reducing tube to the nozzle. Now that thing is just emitting just a small whisper of air. And the nozzle has a larger opening in it, something on the order of about 3/100ths of an inch. So still very small, but not as small as the reducing tube. So as your pressure exits that reducing tube, that whole tube right there is where your back pressure on your flapper nozzle is located. And in other words, the back pressure on this is directly related to the gap between the flapper and the nozzle. So as the flapper comes toward the nozzle, in the case of increasing pressure on the input bellows, the flapper will come toward the nozzle, increasing the back pressure on the relay. The relay is what senses the back pressure from the flapper nozzle. I forgot to show you this one. This shows your input bellows capsule. Got a little ahead of myself. Like I said, there are 5 varieties as listed in that chart. You can replace them for whatever range transmitter you have. And it's pretty simple. You just remove these 2 body nuts, they're called. You remove the connection block, and then you have an O-ring preceding and succeeding the capsule. What's holding the capsule onto the force bar is just a cap screw that you remove with an Allen wrench. A couple of pointers that the instruction manual was very specific to say is do not remove these bolts and do not remove the cap screw from the force bar. You need only loosen it to loosen the flexure on the back of the capsule. I was talking with Mr. Spicer. He's got a lot more experience on these transmitters than I do, and he said that there has been an occasion where he's had to remove the strainer plug, put an Allen wrench up in there, and loosen the cap screw to relieve force on the bellows capsule to get the transmitter start acting right. The only way that I could see that would happen is if that cap screw hadn't been fully tightened in the first place. There is a torque spec on it, and it's in the instruction manual. I didn't include it in the notes, but if that cap screw is seated properly on the back of that capsule, then there shouldn't be a problem. And another pointer is when you replace the capsule, you want to have the transmitter zeroed at atmospheric pressure. You want to have both sides vented to atmosphere. You want to take the zero screw back to where you have 3 psi on the output before you tighten this screw. And the instruction manual says that if you tighten that cap screw and you get less than 0.2 psi change in output, you're good. No other adjustment need be made. But if you tighten that screw and for some reason it changes above 0.2 of a pound, then you got to rethink your strategy. Something is not positioned correctly in this assembly. So, back to the flapper nozzle. Now, like I said, the flapper comes towards the nozzle, increases the back pressure, which is sensed on the relay diaphragm. And here is the drawing of a relay. And I colored the supply pressure yellow as, you know, like a sign that there's energy there. And I colored the exhaust to atmosphere blue. And consequently, yellow and blue make green your output pressure. Because this thing, all that this little pilot valve is doing, I blew it up down here so you can see it a little better. All it's doing is it's moving this shuttle back and forth to either admit more pressure to the output or to bleed it to atmosphere to decrease it. And once it comes into balance, it'll stop moving, the output will stop changing. So this relay, located right here, is made to very tight tolerances. Any dirt or any moisture in the air supply can ruin your day on this. And also, you notice that this relay is kind of small. Everyone's seen pneumatic relays, and they can range in size up to a pretty good size. What you can assume by this relay being small is that it has a small output volume, meaning the output of this transmitter should be connected to something that's going to deadhead, like a pneumatic recorder or a valve positioner, or something that has a bellows in it that doesn't require a lot of volume. If you were to try to hook this relay up to a diaphragm of a valve, it would take a very long time to develop that output signal, because the flapper nozzle pressure would be pushing down hard on this pilot, and it would be admitting as much supply as it could to try to pump up that volume, and you'd see a very sluggish response on the output of the transmitter. So this relay is small because it's not meant to drive anything. It's just meant to go into a dead-headed signal line like a Bellows or something. There are larger relays and there are booster relays for other type applications. Which brings us to our next element, which is the feedback bellows. Now, to recap what we've talked about so far, incoming pressure causes a torsion on the force bar. Force bar goes to the left, so does the flapper. The flapper comes toward the left, developing the back pressure. When that back pressure is sensed on the relay, the output starts to go up. Now, this is the reason this is called a force balance instrument, because when that force occurs, this is thrown out of balance, and the output will start to change. As long as the output is still changing, the system is out of balance. When the output stops changing, the system has achieved balance. And the way it does that is by these feedback bellows. You notice that we have one lever here with a fulcrum here, and that's attached through a flexure to the range bar, which has a fulcrum where the range wheel is positioned. This device right here. When you change the range wheel position, you're changing the span of the transmitter, because you're changing that fulcrum on which that lever works. When the output signal starts to come up, it inflates these bellows and provides an equal and opposite force to the one that the force bar is providing. The force bar is causing the flapper to go toward the nozzle. Your feedback bellows inflates to make that flapper come back away from the nozzle. And where it stops is when this flapper nozzle is balanced. When the output signal, when this force is equal to the force of the force bar, then it's balanced again, and the output will stop changing. Does everybody understand now? The other factor in this is the zero screw. The zero screw is attached to a spring. It's down here. You can see the screw head, but it's very hard to see the spring from here. It's right below these feedback bellows. That provides a preload on the range bar, so that if you crank the zero way up, you're putting a lot of force on the bottom of the range bar, meaning that it will take more force from the process to throw the thing out of balance. That's how you adjust the zero. All you're doing is you're preloading this bar to cause it to require more force to start the output changing.
That's spring tension on the back of that zero adjustment speed?
Yes, sir. Yeah, you can see it right there below the feedback bellows. After the class, you'll be able to look at this a little better, but you see these two screws in this plate, they have a little, like a U-shaped bracket that holds the top of the flexure at the top of the force bar. Those are stops to keep the force bar from moving too much. And you can tell by the small dimensions on that force bar isn't meant to move very much at all. And that's why you can't really see the mechanism working or moving. About the only thing you can see whenever you have the lid off is the feedback bellows inflating. You can see those kind of move a little bit, but this thing is such tight tolerances and so precise that you can't hardly see any movement at all. Let's see, what else am I forgetting about? Well, let's go to the review questions. This is where I get to clean up and remember everything that I forgot. I already gave you the answer to question 1. Whole bunch of reasons why pneumatic transmitters are favorable. Name an example of a force balance mechanism found in everyday life. We looked at seesaws and balance scales. Those are different types of force balance mechanisms. Name some common force balance instruments. Can anyone think of any force balance instruments that are not the Foxboro 11 GM?
Every positioner we got earlier.
Yep, every positioner. The pneumatic ones especially, the ones that take a pneumatic signal on the input, is whenever you put that pneumatic signal on the input of a pneumatic valve positioner, it throws it out of balance. The output relay starts building pressure to move the valve, and the way it comes back into balance is by watching that feedback arm from the valve. That's what causes the valve position to come back into balance. And when it achieves balance again, the output stops moving. Another force balance instrument would be an I to P. An I to P, you just have a big coil and a magnet. Whenever the current signal changes, it throws it out of balance. The pressure output will start to change, and there's a feedback bellows on it to bring it back into balance. What basic instrumentation principle does the Foxboro 11 GM use? Force balance. Thank you. What happens when a force balance mechanism is thrown out of balance? Everyone should be able to recite this by now. The pressure output signal will start to change until the mechanism comes back into balance. And we describe that as the force being exerted on the input bellows capsule has to be balanced by the feedback bellows in order for the output to stop changing. Those are your two main forces in play, the input and the feedback. Number 7, what signal on an 11 GM causes the force balance mechanism to come back into balance? The feedback signal in combination with the preload or the zero adjustment balances the range bar and the output will stop changing. And number 8, what does the span nut do to the force balance mechanism? The span nut changes the moment arm of this lever, creating a different leverage ratio. You see, one thing you have to understand about this device is it's always going to have a 3 to 15 output. So what you've got to do as a technician, or if you're an engineer, what you've got to do is you've got to decide which capsule to use to provide the appropriate amount of force so that the output will stay 3 to 15. This, like I said, everything from here down is the only thing that measures the pressure in the system. Everything from here up is strictly force balance. So if you're dealing with a high pressure, you need a smaller input bellows capsule so that you get the appropriate amount of force on the bottom of the force bar. Because the output of this thing is always going to be 3 to 15. And that's the balancing act. Number 9, what undesirable wear does adjusting the span on the 11 GM cause, and how do you avoid it? I don't know if you can see it from back there, but there's kind of a mirror surface behind this nut where the fulcrum rests on the frame. When you turn that nut, you're causing friction on that mirror surface, and it'll eventually dig kind of a groove in there, which will cause the range to be thrown off. So one way to avoid it is to push just a very slight amount of pressure on top of the force bar, and then you'll be able to reach in there and move that nut relatively free from friction. And one of the things that I was taught way back when was to always remove the pressure input signal. And the reason that is because the pressure input signal causes extra force on this fulcrum. Now, if you're doing a zero and span adjust, you know, you've done your zero, you've checked your span, you're going to have to recheck your zero. So if you have to adjust the span, you're going to let go of the pressure anyway. So wait until you've let go of the pressure to adjust this nut, and that will reduce the wear on that frame element, and it'll keep the transmitter working like new for longer.
One other thing with that, Nathan, as well, the reason you want to reduce that input pressure is that reduces the force on that fulcrum point, right? So you get less galling.
Mm-hmm.
Another thing you can get into is, I don't remember taking apart that flexure, you're taking apart and there's a couple wrinkles on it. You try to adjust that span when you have that force on there, that increased force can actually cause the actual whole arm to move. You can actually end up wrinkling the flexure on top.
This one?
Yes, affecting your linearity and overall span, basically effectively destroying the transmitter.
Yeah.
That's another big reason for wanting to take the pressure off before you turn the span wheel, or the range wheel, excuse me.
Yeah, that's a good point. And a lot of people wonder what this adjustment is for. Everybody see this screw up at the top? That holds no bearing on your calibration. So don't even bother with it. What that is used for, that is used to gap the flapper nozzle when it's being manufactured. If you can see this plate on top, there are 2 capturing screws. When you remove those screws and that plate, then you'll notice that the flexure metal comes all the way out and is captured, it captures that wheel on that adjustment. So without that plate there, the flexure will move independently of the range bar, and you can use this adjustment to zero the flapper nozzle, and then you capture it with the plate again. And at that point, whenever you capture it with this plate, this screw holds no bearing on what you do. It can just sit in neutral and not bother anybody. What can a dirty air supply cause? Well, we already looked at the orifice in this, the reducing tube for the flapper nozzle. It can clog that up in a hurry, as that hole is very small. If that hole gets clogged and you lose your flapper nozzle signal, what do you think the output of the transmitter will do?
months or less.
There you go. It will go low. It will fail low. Because you're not getting any kind of a back pressure signal to your relay. Your relay thinks it's happy all the time, because the nozzle signal isn't changing. And that's where the .0005" wire comes in to clean that orifice. Whenever you have a dirty air supply, you could also clog up the nozzle, but I'm willing to say that you probably clog up the reducing tube first. But if you do end up with a clogged nozzle, you can use a .03" wire to clean out the nozzle. One quick way, and this is another question, one quick way you can tell if you have a dirty air supply, you just walk up to this thing and look at where the flapper meets the nozzle. There'll be a little dirt ring or a little rust ring from where that nastiness has been flowing out of the nozzle. And that's one quick and dirty way you can tell.
Where are you putting that wire through?
On the nozzle?
Yeah,
reducing
tube.
The bottom of it. Did the reducing tube get passed around?
Yeah.
The bottom of it.
Take it out and then.
Yeah, the very bottom of it has like a piece of plastic in it,
Yeah.
with a very small hole in it, and that is the orifice. And you just put that little hair of a wire in there and clean out any dirt that may have accumulated in there.
And that just seeps all the way back in?
Yep. Yeah, you don't have to adjust it or anything, you just thread it in until it stops moving. Of course, you want to inspect the two O-rings that are on it for wear, because they can affect the operation of the transmitter as well. If you're recovering from dirt-induced problems, you can also take the relay off and clean out this block that the relay sits on. The relay mounting block has no moving parts in it. It's just a series of ports to allow the relay to operate and to port the pressure in the right direction. You could also take I wouldn't suggest it, but you could take the feedback signal line off and clean it. I wouldn't suggest that either. Inspect the feedback bellows for any damage. And this relay I've taken apart a couple of times, and there's actually a broken piece inside of this relay. Part of the spring diaphragm, which is that red rubber gasket that you can see there, there's a metal plate that backs it up, and it's got kind of a springy action to it, and one part of it is actually broken. But this transmitter still works perfectly well. That's what I mean, these things are pretty robust. Unless you're trying to destroy them, you're not going to do it much harm. I mean, even if you push on the force bar, it's captured. It's not going to move more than it's designed to move, and it'll be just fine. Where were we? I explained number 11, tell if there's a dirty air supply by examining the flapper nozzle. And how do you recover from dirt-induced problems? Clean the restriction, clean the nozzle if you wish. When you're cleaning the nozzle, you'll notice that whenever you get to look at this, that where the tubing comes into the back of the nozzle, that nut is captured, it's soldered onto the wire, so you don't want to turn that at all. You just want to put a backup wrench on that and turn the nut that is actually on the front of the nozzle. So you got to be real careful that you turn the right element in that you don't break that solder connection. And that's how you can get the nozzle out to clean it. What does the zero adjustment do to the force balance mechanism? It preloads the bottom of the range bar, making it possible to admit higher pressure into the pressure capsule to get the output to change. Can an 11 GM be mounted upside down? Anybody?
Any direction.
Any direction. You just want to calibrate it. wherever you're gonna mount it. For example, if you're gonna mount it like that, you wanna calibrate it like that, should be fine. I tested this in all manner of configurations. I've started by moving it to side. Well, what that does is it causes gravity to affect the force bar, and the output will be thrown out of calibration. So if you're going to use it in this configuration, just calibrate it that way, and it should be fine. But if you take one that's mounted straight up and down and you change its orientation that way, the calibration should shift very little, if at all, because the gravity is still affecting both levers in the same magnitude and the same direction. It's not going to affect the flapper nozzle relationship, or if you mount it upside down, it should be fine. But the way they're designed is to be mounted straight up. What is the rule of thumb for setting supply pressure on pneumatic instruments in general? Anybody?
5 pounds over.
Thank you. 5 pounds over your maximum desired output. So if your range is 3 to 15, set it at 20. If your span is 6 to 30, then set it at 35. What is the purpose of a pneumatic relay? I touched on this a little bit, but let me go into it a little further. This signal on the nozzle has a very small volume. You're just allowing a little whisper of air to come out right here. That's not enough volume to develop an output. But this relay, and that pressure, whenever it goes into this relay, it encounters a diaphragm. And that diaphragm is not going to let any air leak off. So the relay, it takes a signal of a small volume capability and gives it a larger volume capability. And I touched a little bit of that, and that you don't want to hook one of these to the diaphragm of a valve. But if you hooked one of these to a valve positioner, that would be fine. That this thing has enough volume to act on, you know, a long run of tubing and a pneumatic valve positioner, but not a diaphragm. So the answer to that question is it just takes a small volume capability signal and increases the volume capability of it. And we touched on number 17, if a device has a small relay such as the 11 GM, what can be assumed about the device? Well, it shouldn't drive something with a large volume, like a valve diaphragm. It should be limited to input bellows, or something that's going to deadhead the signal so that it can develop an output. What is the purpose of a flapper nozzle? To transform mechanical movement into a pneumatic signal and provide that signal to the relay for the relay to operate. What is the purpose of the range bar? Or no, what is the purpose of the scale on the range bar? If you look at this range bar, I don't know if anybody in the back can see this, but there's a scale along this side of it. And the top of the nut has graduated divisions on it as well. What that allows you to do is if, for example, you're running a batch process where you need to change the span on this transmitter from time to time to allow for different batches, you can just record the number where the range nut stops for a certain span. Like, for example, I have it calibrated for 10 to 40 PSI right now, and the range wheel is sitting at 1.017. 1.017, I could record that number, change the range of it, and the instruction manual claims that when you change the range back to a specific number that you recorded, that you can achieve a 0.5% accuracy if you record the number correctly. And we covered what are flexures. Thin pieces of metal used to transmit force between two elements, where torsion is a factor in movement. So the conclusion, Please use this discussion sheet as a reference to quickly refresh your memory when dealing with any pneumatic instruments or force balance instruments. Please feel free to approach me with any questions you may come up with concerning this discussion. And don't be intimidated by pneumatic instruments. They're really simple and straightforward and fun to work with once you familiarize yourself with them. And that is what I've hoped to do today.
And if I could add to that one, Nathan, it's very true, but the one thing you do have to be aware of when you are working on those, especially around that flapper nozzle, very tight tolerances. So if you work on it, moving that and not returning it to the same position, if the position is off by 10/1000ths of an inch,
Oh, yeah.
you will affect your output greatly. So in working on those, you do need to be aware of how it was before you started and return it to that position. It's just cleaning.
Yeah. Yes, that is a very good point. Very tight tolerances, especially in the relay. If you're dealing with the relay, and let me go back. In this relay specifically, there is a ball for the supply pressure valve. If you loosen this spring that is retaining that ball on its seat, that ball will disappear. It is smaller than a BB. It is very tiny. So any kind of dirt or anything that could affect the tolerances of this valve seat and the ball would be detrimental to the valve, to the transmitter. So my rule of thumb is to leave that spring right where it is. If you need to clean it with no flash or something, squirt it, but don't touch the ball. The ball will be your enemy real quick. You can see in this blown up portion, the atmospheric relief valve on top, it's got very tight tolerances as well. This diaphragm right here only moves just a very minute amount. I doubt you could see how much it moves with your eye. So these are all really tight tolerances. Everything in here is really tight tolerances, so you only want to adjust the things that you know, like the span wheel, the range bar, the fulcrum on that lever, and the zero adjust. That should be the only two adjustments that you have to touch in this thing. And if you do have to touch more, then I suggest getting a vendor manual and brushing up on some of the techniques associated with this. But don't let pneumatic instruments intimidate. Now, once you remove the cover, you can see everything in them pretty much. I mean, on a Fisher valve positioner, for example, you remove the cover, it's got that deal that looks like a protractor. Well, that's just a fancy lever. You've got a feedback bellows affecting it, a feedback cam that is the valve position, and that throws it back into balance. When it's back in balance, the output stops changing. Thank you.
Thank you.
Any questions?
Number 6,
Number 6.
is that the Bellows capsule?
Yes, the input pressure signal acts on the force bar, causing the mechanism to be out of balance. And we know that force balance mechanisms, when they are thrown out of balance, the output starts to change. Any other questions?
Who invented those, do you know?
I don't know. Somebody with lots more brain cells than I'm capable of mustering up. This transmitter will be out in the shop. I'm going to put it in a vise, and if you want to look at it and tinker with it, feel free to do so. This came off of a nitrogen cart, so it's old. It's a little worn out. There are a couple of dents and bruises in it, but it still works really well.
Thank you.
Thanks, Nick. That's all I got. Let's have a safe day out there. Thank you.
Pardon me? I think you're older than me. Thanks, man.